Okay, we first review some basic concepts about sets. Okay, a set is just a collection of elements which have the same or a common properties that is specified. So, for example, A is a set, and we use this notation to denote that it's a collection of sets, a collection of elements, we denote by X, that have the same property. Okay, example of this is that A is, for example, A is all the real numbers that are greater than a square is greater than 1. So that's just the union of these two intervals, right? So I'm specifying this should be just Rn. All right. So there are some basic operations about sets. So intersection, or A. Sorry, the subset of A is a subset of B. It just means that every element in A is also in B. So if I draw a picture of that, it just means that this is the B and this will be the A. Okay, so every element in A is also in B. The union of A and B is just all the elements that are in A or in B. Okay, so the picture, we can show the picture. If this is the A, this is the B, then the union of them is just all the area they can cover. Intersection is the elements that are in A and also in B. Okay, and from the picture, that means if this is the A, this is the B, then it's a common area. The complement of A is all the elements that are not in A. Okay, so this usually refers to the case that we have a universe X. It's just all the things that we can consider in the context, and that the A will be just a set inside it, and then the A complement A will be everything outside of A. Empty set is just a set that contains nothing. Okay. When we talk about the set A equals to set B, it's not really the sense of equal for numbers. It just means that the two sets have exactly the same elements. Okay, so that just means that A is a subset of B, and also B is a subset of A. So they just have the same elements. Oh, by the way, we use this subset notation. Say A is a subset of B. So A could be a proper subset of B, or A could be just equal to B. So sometimes you see notation like this. That's the meaning. That's the same meaning as I just said. But in this book or in this class, we just use this notation. Okay, if you want to denote, you want to specify that A is just a proper subset of B, then we can use this. It means that A is contained in B, but A is not exactly equal to B. Okay, so that's just some common notations you see in different books. Okay, the last one is the side minus, so that A minus B, side minus. And this is just the set of elements that are in A but not in B. Okay, so you can usually write this as the intersection of A and B complement. So what that means is you have this A here, you have this B here. Then the A minus B will be the area in A but not in B. Okay, so it'll be this shaded area here. So that's the side minus. Okay. You can see more examples. Okay, when you take intersection of two sets, you will always get a smaller set, or at least it cannot be increasing, right? So if we take the intersection of A and B, then this set will be contained in A and also in B. Say it's contained in A. And if you take the union of A and B, then you usually get, you will not get a smaller set. It will just have more elements included. So the union will generally give you equal or larger set. Okay, so for any set A, it contains the intersection of A and B, and it contains the intersection of A and B that is also contained in the union of A and B. Okay, so that's one example. Another way to say that A belongs to B or A is contained in B is that B complement is contained in A complement. So you can see this from the Venn diagram, which is this is the X, say this is B, this is the A. So as you can see that if A is contained in B, then the complement of B will be everything outside of B, and that is contained in the A complement, which is everything outside of A, right? So this is actually pretty straightforward to see. A and B do not overlap. So there is another way to say this. If A and B are not overlapping, then you can see from the picture here, this is again X, and A is here, B is here. Then A will be contained in the complement of B. So the complement of B is everything outside of B. So apparently A is a subset of that. Okay. A slightly tricky one here, but very simple, still very simple observation here is that if you have two sets, A and B, they are both subset of the X. And if for any set in X, you have, let me remove this. The intersection of E and A is equal to the union of E and B, then it just means that A is the entire set X, the B is empty set. And you can see this by taking E as, for example, you can take E as empty set, and then the intersection of E and A will be just empty set, right? And you take the union of E and B will just be the self, because E is empty. So that means this will give you just an empty set, and on the right hand side it will just give you the B. And these two are equal, that means B is an empty set. And similarly, if you can set E to the X, then on the left hand side you see that the intersection of X and A will be just A itself. And the intersection, the union of X and B will be just B. right? Because X is the largest set. So that gives us that A is equal to X. Okay, so you can prove that easily by this. We often consider the collection of sets. So we call it the collection of sets. It's just a set of sets. Just avoid the cumbersome of the name. So you have this F. It's a collection of sets. It just means that I have something like this. So here, A alpha is some set, and alpha is the index. And this I, the capital I here, is the index set. So for example, if you have a finite many of sets here, then this I will be just 1, 2, depends on how many you have. You have 10, it's just 1 through 10. But in general, you have n of them. Or this I could be the set of natural numbers, which is 1, 2, 3, 4, right, to infinity. So these two types of sets are called countable. Means that you can enumerate it by natural numbers. But there's also a case that the I is uncountable. So we'll talk about what the meaning of uncountable later. Here, it just means that I could be something like that. It could be, for example, the interval from 0 to 1. Okay, this is actually uncountable set here. Okay, so a collection of sets could be like this, could be written in this way. And with this, you have lots of sets here. So you can take the union or intersection of them. So for example, you can take the union. And this just means that all the elements that is in one of them, at least one of them. Okay. Okay. You can also talk about the intersection of them. Say this. And this just means all the elements that are in all of those sets. Okay, so we usually deal with this kind of unions and intersections. So just try to get familiar with them. Important property of these operations, the intersection and the union, is that you can apply the distribution law. What that means is say you have a set A and you have a family of sets B alpha, and you take the union of those B alpha. Okay, again, this I could be countable, could be uncountable, could be finite. So this union of them gives you a set, right? And then you can take the intersection of these two sets, A and this. So the distribution law says that you can distribute this this A to those B alpha. So what that means is this intersection will be just equal to the intersection of A with each B alpha. Okay, and similarly, if you take the union of A and this intersection of B alpha, and then you can distribute A to those B alpha again, and you have, oh, I'm sorry, here it should be the union, and here this should be the intersection of A union B alpha. Okay, this is called the distribution law. So you can have, again, you can have a finite many of the B alpha or infinite many of them. Okay, and this will always hold. Now let's see some examples. So suppose AK is this kind of interval. Okay, you can see that this just you have just A here, this is B here, and A plus 1 over K is something like this. So this is A plus 1 over K, depending on the size, depending on the value of K. So it just give you this interval. So this is my AK, and the K is the index, right? And then you can think about the union of them. So if I have this, then I take the union of AK. So you can see that if K gets larger and larger, the 1 over K gets smaller and smaller, and eventually A plus 1 over K will get closer and closer to A. Okay, so this is actually equal to this. Okay, the reason is that first of all, A is not included because you can see that A itself is not included in any of those AK. And on the other hand, any number that is bigger than A, so any number that is bigger than A, so it doesn't matter how close it is to A, say it's something here, I call it A prime, and then you can find some K large enough so that the A plus 1 over K is between A and A prime. Okay, so you can find some K large enough such that A plus 1 over K falls in between this. That means A prime will be included. So everything that is bigger than A will be included in this union, but A itself is not included. So that means the union of them, it gives you this half open, half closed interval. Okay, and similarly, if I have the A as this, and then I consider the intersection of this AK. So again, this is the A, this is the B, and the B plus 1 over K will be something like this. And I remember that they're all open. So when I take an intersection of those AK, you can see when I get K larger and larger, this B plus 1 over K will get closer and closer to B. Right? And then when I take the intersection of them, I'll get A, B. Again, the reason is that you can see B is included in every one of them, every AK. So it will be included in the intersection of them. But on the other hand, every number that is bigger than B, I can find every number that is bigger than B, let's say this is B prime, I can find some K large enough so that B plus 1 over K falls in between B and B prime. So that means the B prime will be not inside AK, and it cannot be inside the intersection of AK. So another example is, say I have index set that is uncountable. Say I have this A alpha is denoted by 1 and negative log of alpha. Okay, and this alpha belongs to the index set, which is all the real numbers between 0 and 1. Okay, remember that this is the uncountable. This is the uncountable set. Okay, so then if I take the union of A alpha, what will we get? So first we recall that if I have a 0, 1 here, and then the log of alpha, this is alpha, the log of alpha will be, negative log of alpha will be like this. Right? So this curve here is negative log of alpha. So if your alpha is between 0 and 1, like here, then this negative log of alpha will be from 1 to positive infinity. So if I take the union of them, I'll get all the numbers from 1 to positive infinity. So they will give me just 1 to positive infinity. And on the other hand, if I take the intersection of them, then I know that the negative log alpha is any number from 1, including 1, to positive infinity. So I take the intersection of them, I will just get 1 itself. So it's a set that contains 1 only. So another example is, say I have a function from this interval to R. So what that means is I have this function here. This is the A, this is the B, and then my function is just like this. So here, this is my function fx. Okay. So now, consider this set. Which are all the points over the interval such that f of x is bigger than 0. Okay? The absolute value of x is bigger than 0. So it's bigger than 0, that means it could be any number, right? Bigger than 0 as long as it's not 0. So I could say that it's the union of all such sets. Okay? I can even put this as bigger than or equal to. So the point here is that if f of x is bigger than 0, absolute value is bigger than 0, that means it is some positive number, right? It's a positive number, that means you can always say have it's the x, it's the f of x. So if it's for some point x, the value of f at x is bigger than 0, then that means it is bigger than some 1 over k. Okay, so you take the union, that just means that it's any number between a and b such that f of x is bigger than the 1 over k. Okay, the Morgan's law is a very helpful, useful result about to interchange the union and intersections. So suppose I have intersection of some sets. Then I take the complement of that, and then I can put this complement on each of those sets, but I need to change this intersection to union. Okay, and similarly, if I have a union of them, and then I take the complement, then I can change the union to intersection, but I also need to put the complement on each of those sets. Okay, limits of sets. Okay, consider the case that we have a sequence of sets, the A1, and that contains the A2 and contains A3, and some of them could be equal. Okay, as I said, this notation means that it's a subset, but not a necessarily proper subset. So this I have a sequence of sets like this. Then in this case, we say that AK is non-increasing. Okay, and similarly, if I have the sets like this, then it just means that AK is non-decreasing. Okay, and in either of these two cases, we can talk about the limit. For example, in the first case, if it's non-increasing, I can also use this notation, and this limit of AK, because it's non-increasing or it's decreasing, so the A1 is contains A2, A2 contains A3. So the limit of this is just the same as the intersection of them. If these AKs are non-decreasing, so A1 is included in A2, A2 is included in A3, then the limit of them is just the union of them. Okay, so this means the limit. This is the meaning of the limits of sets, but only if they are monotone. Okay, let's look at an example of this. Say I have the AK as intervals k from k to positive infinity, and again this is some interval on the on a set of real numbers. Then as you can see, when I have k getting larger and larger, then this AK gets smaller and smaller. So actually the AK is non-increasing, right? So the AK decreases as k goes larger. Okay, and then in this case, the limit of AK is just the intersection of AK. But you can see that the intersection of those AKs will be empty, because as k gets larger and larger, the intersection of them will be just covering nothing. Okay. Another example is, let's say we have a sequence of functions. I have the f1, f2, f3, and they are not decreasing. So it's like this, 2. And also if fk is converging to f. So in this case, we can simply denote this by fk goes up to f. Okay, and now for any t, let's say I defined AK to be the set of X such that Fk of X is bigger than T. Okay, this is just a collection. This is only related to, it only depends on f of k. And it's the old X such that Fk of X is bigger than T. Okay, I'll claim that this AK is non-decreasing. The reason is that your f of k is getting larger and larger. So if there's some x that belongs to AK, that just means that fk of x will be bigger than t. And if fk of x is bigger than t, then fk plus 1 of x will be also bigger than t, because the sequence f is non-decreasing. And this just means that x is also in AK plus 1. And this means that AK is a subset of AK plus 1. Right? So the AK is actually non-decreasing. And then we can talk about the limit. And the limit of AK will be just the union of AKs. Okay, and notice that the I'll claim that this is just the set here. Oh, sorry, I will not have the absolute value. Okay, it is obvious that the left-hand side here belongs to this side. So I should have this here. Okay, but the question is, how do we show the other direction? How do we show this? How do we show that right-hand side is a subset of the left-hand side? So how to show this? So here's the idea. You look at this left-hand side. This is all the x such that f of x is bigger than t. So if I draw the picture, that means, say this is t. This will be f of x. So if f of x is bigger than t, then that means and your f of k, f sub k of x is converging to f, is going up to f of x. That means up to some point, it will pass through this t. Okay? So for k large enough, your fk of x will be somewhere here. Right? So that means if x is in this set here, then that means for k large enough, x will be in one of those ak. Okay? Formally speaking, that means you can think epsilon to be 1/2 of f of x minus t. So the epsilon will be the gap here. So half epsilon, the epsilon will be half of the gap here. Half of the gap here. So this will be my epsilon. So it's a half of the gap. And then for k large enough, f sub k of x will be bigger than f of x minus epsilon. So for k large enough, this f of k of x will be bigger than f of x minus epsilon. The reason is that f sub k is converging to f. So that's why this is true. Okay, and therefore x must be inside a k. So for any x on the left-hand side in this set, it will belong to one of those ak and eventually. So that means this right-hand side will be actually a subset of the union of ak, or the limit of ak. So this proves that these two sets are equal. Okay, so this is just equal to this set. Okay, our next definition or concept is the so-called upper limit and lower limit of sets. So previously we have a sequence of sets which are monotone, so they're either increasing or decreasing. But in general, we may just have a sequence of sets, but they're not necessarily monotone. In this case, we can still consider limit, but it would be upper limit and lower limit instead. So the upper limit is defined in this way. So first, think that I can define this Bj is a set that is taking the union of those AKs for k from j to infinity. So it's just taking the union for ak, ak plus 1, ak plus 2, so on and so forth. So that's my definition of Bj. And now you can realize that the Bj is non-increasing, or it is decreasing. The reason is if you increase j, then you increase j here, then you'll be taking union of fewer sets of ak, right? Fewer AKs. So that's why when j increases, the Bj will decrease. It will be a smaller and smaller set here. So because the Bj is monotone, it's decreasing, so you can consider its limit as before. So the limit of Bj, as a decreasing sequence, the limit of Bj will be just the intersection of those Bjs. So the limit of the Bj is just the intersection of those Bjs. And then you substitute this definition of Bj here back into this Bj. Then you replace the Bj by that. And this is the definition, is the upper limit of the sequence AK. So this is definition for upper limit of the sequence AK. So AK doesn't have to be monotone, but you can still define this upper limit of the sequence. And similarly, you can define the lower limit. In this case, we'll be defining this bj as the intersections of ak. So again, the intersection is taking over all the j's to infinity. Okay, so it's just the intersection of ak, ak plus 1, ak plus 2, so on and so forth. And now instead of as you can see, when the j is increasing, you're taking intersection of fewer sets, which means that you potentially will get a larger set of bj. So in this case, when j increases, the bj will increase, or bj is non-decreasing. So bj is a non-decreasing sequence along j, and then we can also talk about the limit of the bj. Since bj is increasing, the limit will be just the union of those bj's, and then we substitute the bj back. So the bj is here. I'm going to substitute it here. So you can see that the bj becomes the union of bj becomes this, and this is called the lower limit of ak. Okay. So how do we interpret this to the upper limit and lower limit? So recall that I'm just repeating the notation of the upper limit is this one here. So you can see that when x belongs to this, so first of all, this is a set, right? It's taking a union of a bunch of sets, and then this is still a set, and take the intersection of those sets. So still this is a set, and x belongs to this set means that you see here you have the intersection, which means that the x has to be in all of, if you treat this as the bj, then x belongs to this means that x belongs to all of those bj's, right? Because this is called bj. So the intersection of that means x belongs to every bj. Okay, and then once you have the j, you can see that x belongs to one of those ak's. Okay, because k from j to infinity, this is the union. So that means for each fixed j, x is in one of those ak's. So in summary, what we have here is that if x belongs to this set, that means for any j, because it needs to be in any, this has to be in any j because the intersection. So for any j, there exists some k. So any one of them, the k, as long as k is greater than j, then x should be inside ak. Okay, so this intersection is translated to for all, and this union is translated to exists. So the x belongs to the upper limit of a k, or belongs to this, means that for any j, there exists some k such that x is in a k. Okay, I can do this. We can do the similar thing for the lower limit. So in this case, the lower limit is defined as this set, and as you can see here, you have the union and you have the intersection here. So for union, we'll translate it into exists, because it just needs to be in one of those j. Just needs to be true for one of those j's. And here, this is the intersection, and that means it has to be true for all the k's bigger than or equal to j. So there exists a j such that for any k greater than or equal to j, there is this x belongs to a k. Okay, so x is in the lower limit means that there exists some j such that x belongs to a k for k greater than or equal to j. So what's the difference here? As you can see, the first one right here tells you that if you have this sequence listed, you have ak, b, say a1, b, a1, a2, a3, a4, a5, so on and so forth, then this means that it doesn't matter how large this j is, there will be always some k that is bigger than j, such that x belongs to ak. So that means this x belongs to infinitely many of those ak's. Okay, so you have a1, a2, a3, a4, a5, a6, so on and so forth, but this x will be inside infinite many of them. It doesn't matter how far or what is the gap between the two. Maybe x belongs to a2, then a5, and the a10. It doesn't matter how much gap they have in between, as long as your x is in the in infinite many of them. or in other words, x is in the subsequence of those AKs. So this is the definition for upper limit. So x belongs to the upper limit if x belongs to infinite many of those AKs. Now we compare to this one. This means that starting from some j, the x must be in all those AKs after j. So that means x needs to be in aj, aj plus 1, aj plus 2, and all of them. So this is different from the one here, right? You can see that. So you have a1, a2, a3, a4, a5, but up to some point, x must be in everyone after that. Okay, so this seems to be even stronger than this one. So this one is even stronger because the x will be inside every AK starting from some k. Okay, starting from that k. So it is easy to see that the lower limit is a subset of the upper limit, because if x is in the lower limit, it will be inside AK. It will be inside all of those AKs starting from some k. So that definitely is a subsequence of AKs. That means x will belong to this as well. So if x belongs to this set, then you can easily show that x belongs to this set. Then that means this is a subset of this. Okay, so let's look at a few examples. So suppose we have a sequence of functions. Fn is a sequence of functions, and we have this f. So now let's consider this set. So since we have sequence, we can consider the limit. Maybe they exist, maybe not. But for any x, we can consider a sequence of numbers, which we call fn of x. Now, as n goes to infinity, we can check if the limit is equal to the value of f of x. And the question is that the problem we are trying to prove is this set is actually just equal to this set. Okay, the left is equal to the right. Okay, so why this is true? Remember that if a sequence is converging to, if sequence fn of x is converging to f of x, so let's say for any fixed x, let's consider the sequence of fnx. And if they converge to fx, that means, by definition of limit, that means for any epsilon, there exists some integer capital N, such that for any n greater than equal to the capital N, there is this quantity here. This is the definition for limit, right? So this is the definition for limit. But what if the fn doesn't converge to f? Fn doesn't converge to f of x. We will just need to reverse this definition here. So if it doesn't converge, that means there exists some epsilon, we call it epsilon 0, such that for any n, there exists a little n. You can see that this is replaced by for all. That existence is replaced by for all, and for all, for any, is replaced by the exists. Also, this for all is replaced by exists. So this is just a revert the statement here. Okay, since we're thinking about the sequence fn not converging to f. So this is essentially the definition. So that means for any, there exists some epsilon 0, such that for any capital N, there exists some little n, such that this is greater than the epsilon 0. Okay, so now remember previously we have shown that if you have this epsilon 0, there exists some epsilon 0, or this for all epsilon, you can replace the epsilon by 1 over k, because you know k is integer. So 1 over k can be arbitrarily small as you want, right? So there exists some epsilon greater than 0. That means there exists some 1 over k greater than 0, such that this is true. Okay, and so we can just replace this by that there exists integer k, such that for any capital N, there exists a little n greater than the capital N, such that this is greater than or equal to 1 over k. Okay, so now we'll just replace this by k, and this will be 1 over k. Okay, and if that's the case, then remember that I can always rewrite this existence by union, right? There exists k means that it just needs to be true for one of those k's. And then for any n becomes that, right, becomes intersection. And for any, there exists little n bigger than capital N. That means you're taking the union of the little n from capital N to infinity. And then this part would be bigger than or equal to 1 over k, and that's what I copy here. Okay, so this not if x, if fn is not converging to f at this point x, then that just means that this is true. So I collect all those points x, and then take this. This will be the set where x is not converging. The fn of x is not converging to f. That's why this is just equal to that. Okay, and this is essentially just the right hand side. Okay, now let's look at another example. So say we have a sequence. Again, I have a sequence of f that converge, sequence of fn that converge to f at every point, and then for any real number t, there is this set. So this is a set of points where f is less than or equal to t. Okay, and we can show that this is just equal to the right hand side. Okay, so again, how do we show this? Look at this we call this left hand side. Left hand side is because the fn is converging to f at every point. So this fx is just the limit of fn of x. So I just replace that by fn of x. So this is less than or equal to t means that the limit of fn of x is less than t. Fn of x is less than or equal to t. Okay, so if the limit is less than or equal to t, what that means is if the limit of these numbers is less than or equal to t, that means for any epsilon, there exists some capital N such that if little n is greater than or equal to capital N, we will have this. Right? So this means the limit is less than or equal to t, and then that just means that this will hold. Okay, and similar as before, we can replace this epsilon by 1 over k. So that means for any k, for any integer k, there exists some capital N such that when little n is greater than or equal to capital N, fn x will be less than or equal to t plus 1 over k. So for any here becomes the intersection, the epsilon becomes 1 over k, right? So this for all becomes intersection, there exists becomes this union, and then for all the n, this I should have for all the n greater than that capital N, that becomes intersection, and then we have this. Okay, so the right hand side, this is exactly the right hand side we have here. Okay, that's the another example. Okay, so this is actually very important and useful later on in this class. When you see some sets like this, you can always convert it into this form. And also, similar as the previous example, for all the points that the f is not convergent, you actually can show this to or equal. Okay, so this, if you want to characterize where the function fn is not convergent to f, then you just can characterize this set by the right hand side, and you can study the right hand side. And the benefit of the right hand side is that you see here it only depends on this integers, and the integers they will be only finite. It will be only countable in many of those integers. Then that's much easier to deal with than dealing with this epsilon, which is it's a real number. It's in an uncountable set of real numbers. Okay, so you'll see this later on in this class, and we'll be using it again later on in this class. Okay, So before we close this section, I give the last definition is called Cartesian product. So we have two sets, for example, have two sets A and B. Then Cartesian product of these two sets is just this kind of pairs. It's ordered pair where the first argument is from the set A. The second argument is from the set B. Okay, so the Cartesian product of the sets A and B is just the set of those pairs where the first argument is from the set A, the second argument is from the set B. So this is different from the Cartesian product of B and A. So that's, you can see that would be different because the order is changed. Okay, but other than that, this is very straightforward to interpret it. So for example, if I have this set A as just the set of the three numbers, B is the set of these two numbers, then Cartesian product of these two will be 1, 4. So the first argument must be from the set A. The second argument is from the set B. So it's 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. Right? So that's the Cartesian product of A and B. If you switch these two, as B, Cartesian product of B and A, then you will still have 6 elements, but they're all different from these 6, right? Because the first argument has to be 4 or 5. Okay, that's one example. Another example is that A is the interval 0 to 1. It's a closed interval 0 to 1 in R. Okay, and the B is the same one. It's also a closed interval 0 to 1. And the cross product of, or the Cartesian product of A and B is just the Cartesian product of these two intervals, and they will become, usually it's written as 0, 1 squared. And what that really means is this is a pair of numbers, x and y, where x is from A. So this is from A, and this is from B. Okay, but A and B are the same, so x and y are both from this set. Okay, so that's the Cartesian product of these two intervals, and what that translate into is that A and B are both this closed interval on the real line. So this is the whole real line, and this is the interval A or B, interval 0 to 1, which is A or B, and the Cartesian product of this becomes this, which is the square on the two-dimensional Euclidean space. So this will be the A, this will be the B. The Cartesian product is this square. Okay, so that's the example for a Cartesian product. Okay, now we start to review the definition for functions. So we say the function f is the function of f is a mapping from the set x to the set y. So you just have two sets, and the function is defined as a mapping from x to y. So what that means is it takes every element in x to some element in y. Okay, so we call this f as a function or mapping. So for every point in x, it will be mapped to some point in y. So say you have another point here, and it can be mapped to some different point in y, but it can also be mapped into the same point in y. But the only thing I cannot do is that if have f, if at some point in x it can only be mapped to one point in y, cannot be mapped to another one. So for every point in x, there exists a unique point in y that can be mapped to. Okay, so that's the function f. Then we can talk about the concept of image and inverse image. So the image of f usually refers to a set. So let me draw it here. So say I have this set x, and the A is a subset. Now what's the meaning of image of f under image of A under f is this. So I have this x and I have this y, and the image of A under f is just the collection of points in y which correspond to some point in x. So this is f of A. Okay, and this f of a is called the image of a. You can specify that it's under the mapping f. Okay, so that's the image. The pre-image is this. Pre-image, or the inverse image, sometimes it's also called pre-image, is defined in this way. You have a subset in Y, they call it B, and then the inverse image or the pre-image of B is defined as the points in X such that it is mapped to the B. So the inverse image of B here, F inverse is written as F inverse of B, is the collection of points in X who are mapped to some element in B. Okay, so that just means that these are the points that will be mapped to B. All the other points outside of this will be mapped to some other point here. Okay, so that's the inverse image of B. So the image of some set in X, like in some set in X, say A in X, is this. And the inverse image of some set in Y is like this. Okay, so that's the image and the inverse image. Okay, notice that the image here, so the image of that is this. But since different points can be mapped to the same point, different points in X can be mapped to the same point in Y. So there could be some other point here that are also mapped into this. Okay, so the image of A is just collecting what can happen to the points inside, but it doesn't matter what the outside is. So it could be some points could be mapped to there, this one here. But for inverse image, you have this. Then the inverse image contains all the possible points that will be mapped to here. Okay, even if you have 2 points that are mapped to the same point in B, then they will be both in the inverse image. Okay, so that's the inverse image and the pre-image or inverse image. We also talk about given the function, we also say that function is surjective. So what that means is simply just the fx is equal to y. That means the fx will fill up the entire y. Okay, so the function is surjective if f of x is y, or the image of x is y. The function is injective, means that 2 different points will be sent to 2 different points in y. So you will not see something like I have 2 points and they're both sent to the same point in y. So if the function is injective, then if you have 2 points in x, then they will be mapped to 2 different points in y. So this is usually defined as, say, f is injective if x equals to x different from y implies f of x different from f of y. Or sometimes this one can be also written as if fx equals to f of y, then that means x must be equal to y. Okay, either one of them. So that's that's the definition for injection. Okay, so notice the difference here. If the function is both surjective and injective, then we call the function a one-to-one correspondence. So as you can see, if some function is surjective, that means this f of x will be the entire y. So that means every point in y, there will be some point in x that is corresponded to. And also the function is injective, that means everyone in x must be mapped to a unique point in y. And also a different point in x will be mapped to a different point in y. So now you can see that why we call it one-to-one correspondence, because that it seems that it appears that we can have a correspondence between every pair of points in x and y. Okay, so if the function is surjective, then we call it one-to-one correspondence. So in the 1D case, So for example, f is function from R to R. So let's say f is function from R to R. And then say the function looks like this. Then we can say this is injective. Let's just focus on the injective part. So the function will be injective here because for every value of f, it only corresponds to one point in x. And this is different from this example where the function looks like this. And you can find some point f of x, some value of f of x, such that it corresponds to more than one point. It corresponds to these two different points. They both have the same function value. So this is injective. This one is injective, but this one is not injective. And then if this is filling up the entire interval, then it is also one-to-one correspondence. For example, if the function looks like this, they fill up the entire real line, then this function f is injective, is one-to-one correspondence. If the function looks like this, it's not really going to fill up the entire y direction, then this function is only injective but not one-to-one correspondent. Okay, so that's one-to-one correspondence that we just mentioned. It's if the function is one-to-one correspondence, if and only if this function is surjective and also injective. Okay. In particular, in this case, if you have a one-to-one correspondence, then we can actually define the inverse of f. Because you have one-to-one correspondence, then you have a point x here, then you have another point y here. And since then we can, for every y here, we can define this as the as what you get by mapping. So if from this to this is the f, and if from this point to this, we can define it as f inverse. Okay, and remember this f inverse, this is actually the inverse of f. That is different from the inverse image here. Even if f is not injective or one-to-one correspondent, we can still define the inverse image, even if because this it just tells you that what is the set is. You could have two different sets here that are mapped to the same point in B. It's okay because this is just giving you a image. It's just giving you an inverse image, which is a set. But this is different. If you have one-to-one correspondence, you actually can define the function because you will not have the case as before that the same point. Two different points are mapped to the same point here, and you don't know what is inverse is. You don't know which one is corresponding to. We take the inverse. Okay, so that this is different from the previous one. This is the current one is much nicer. The f is one-to-one correspondence. That means you actually define the inverse of this function. Okay, so although we have this f -1 notation, but this has different meaning. It's a function here for the one-to-one correspondence f, but this is just giving you a notation. You have to give what is b here to make this to make sense about this. Okay, and then we can also define the composition of functions. So I have two functions f and g. And f is a function from x to y. Okay, and g is a function from y to z. And then we can do the composition of them, and this is denoted by g composed with f. Okay, and the meaning is that for every point in x will be mapped to a point in z, and how that was mapped, the x will be mapped to this. So you first apply f, then you get a point in y, and then you apply the g. So it's like this is the x, this is the y, and this is z. Your f is mapping from have x, y, z. So you have x, and that will be mapped to some point f of x here by f. And then this point will be mapped to some point here. It's g of f of x by this g. Okay. usually when we talk about the composition of the functions, you know that when the f is surjective, that will be no problem at all, right? If f is surjective, then that means f of x will fill up the entire y, so there's no problem. If f is not surjective, then f of x will be just a subset of y. It will be a subset of y, and the g could be still defined over the entire y, but you will not get the value outside of this image of x, not outside of this circle. But that doesn't matter, because we take the g on f of x, and f(x) has to be something that is mapped from the x. So the g will be just restrict to this part. Outside, you will not, when you take the composition, you will not insert any value outside of the circle, because this f(x) is is in the image of x. Okay, so let's look at an example of that. Okay, suppose I have a set A in X, subset of X, subset A in X, then the characteristic function of A is defined as this binary function. So this binary function for any point in X, for any point in little x in the set X, I will get the value 1 if this X is inside the A, and it will be 0 if X is outside of A. So you look at the image here. This is the X. This entire set is X. A is a subset, and this characteristic function of X is just that it takes value 1 here and takes the value 0 outside of A. Okay, an easy observation you can have is if this is the characteristic function of X, then the characteristic function of A complement will be just 1 minus this, because the A complement will be everything outside, and the characteristic function of that will be taking value 1 outside of A, but taking value 0 inside. So just the reverse of this. Okay, so that's why the characteristic function of A complement will be just 1 minus the characteristic function of A. Okay, and based on this, we have several simple properties about this characteristic function. If A is a subset of B, then the characteristic function of A will be less than or equal to the characteristic function of B, and that is clear, right? If X is in A, then both sides will be 1. If X is in A, is in B but not in A, then the left-hand side is 0, or right-hand side is 1. If X is outside of B, then both sides take value 0. Okay, so this left-hand side is always also is less than or equal to the right-hand side. Okay, and then let's say the characteristic function of the union of A and B. So the union, if this is the X, A is here, B is here, the union of A, B will be just this area. Okay, the characteristic function means that you take a value 1 here and take a value 0 outside. Okay, now you can see that if you this left-hand side is actually equal to the right-hand side, which is chi A, or the characteristic function of A, and characteristic function of B, and the minus characteristic function of A, intersection of A and B. So why we're doing this here is because, say, on the left-hand side, if X is in the union of A and B, then the left-hand side is 1. Okay, so if X is in the union of B, it will be either in A, it will be here, or here, or here, right? So if X is in A but not in B, then you have this as 1, this as 0, and this is 0. So the right-hand side is also 1. If X is in B but not in A, then you have this as 0, this as 1, this as 0. So again, you have 1 on the right-hand side. If X is intersection of A and B, so it's in A and also in B, and this is the 1, then this is also 1. So you have 2. Then you need to take 1 out. Okay? If x is in the intersection of them, you still have 1 on the right hand side. If x is not in the union, that just means that it's not in here, it's not in A, it's not in B, it's not in intersection of A and B either. So on the right hand side, you will just have 3 zeros. So you get 0 on the right hand side. So that's why this identity holds. Okay, next, the characteristic function of the intersection of A and B. So x will take a value 1 if it's in the intersection. It will take a value 0 outside. So it's 1 when it's in the intersection. So that means it only takes 1 when it's in A and also in B. So that is just the product of these two characteristic functions, because only when x is inside A and also inside B, you have both of them as 1. And then the product of this is 1. If x is just in one of them or in none of them, then the product here will be 0. Okay, the characteristic function of A minus B. So remember that, this. The characteristic function of A minus B is just taking value 1 here and 0 outside. Okay, just taking value 1 here and 0 outside. So remember that the characteristic function, the A minus B is just the intersection of A and B complement. So essentially, following the previous one here, this is just the A intersection of A and B complement. That's why it's just chi A times the chi of B complement. But the chi of B complement, characteristic function of B complement, is just 1 minus characteristic function of B. So that's why we can replace this one here by this. Okay, and then you have that. So that's you can replace this characteristic function by this. And also the symmetrical difference of A, B. So the definition of symmetrical difference of A, B. So you see a triangle in between A and B. That's called a symmetrical difference between A and B. So what that means is it's a collection of elements that are in one of these two, but not both of them. So if I draw a picture, then this will be A, this will be B, and the symmetrical difference of A and B will be this area and this area, because it will be only in one of them, but not both of them. So this can be written as A minus B, so it's in A but not in B, or it's in B but not in A. So take the union of these two. Or you can take this as the union of A and B minus the intersection of A and B. So it's inside one of them but not inside both of them. Okay, you can easily show that these two are actually equivalent. They are both definition for symmetrical difference. And now consider the characteristic function of the symmetrical difference here. You take a value 1 in this part or this part, and take a value 0 here or here. Okay, and then you can actually verify that this holds. The characteristic function of the symmetrical difference of A and B is just the absolute value of the difference between these two characteristic functions. The reason is if x is in A but not in B, then this is 1 and this is 0. Okay, you have 1 here, you have 0 here. So the absolute value will be 1. If x is in B but not in A, then this will be 0. This will be 1. Okay, so you again get 1. If x is in both of them, both of A and B, then this will be 1, this will be 1. So the cancel out is still 0. If x is in none of them, then we'll have 0 here and 0 here. So it's still 0 on the right hand side. That verifies this identity actually holds.